40 kilograms of water every single second. That is what NASA's Swift Observatory detected pouring off 3I Atlas in late July and early August. Not at perihelion, not when the comet was kissing the sun and maxing out on solar radiation. At 2.9 astronomical units, almost 3 times farther from the sun than Earth, where water should barely be sublimating at all. And in less than 3 weeks, it vanishes behind our star, hidden from every telescope on Earth, right when things get most intense. If you want to stay updated on what happens next, hit that like button and subscribe. Tell me in the comments where you are listening from, what time it is there, and whether you think this is just extreme commentary activity or something else entirely. Chapter 1: The Fire Hose Mystery. The Swift observations published September 30th in Astrophysical Journal Letters are not just unusual. They are breaking the rules. Dennis Boditz and his team at Oren University spent over 2 hours stacking ultraviolet exposures to catch the hydroxyl signature. That telltale glow left when sunlight tears water molecules apart. What they found was a mass loss rate that defies distance-based predictions. At that range from the Sun, comets typically show 3 to 5% surface activity, 3I Atlas at least 8%, nearly double. But here is where it gets strange. The math does not work for pure surface sublimation. Even accounting for solar heating at 2.9 AU, the energy input is not sufficient to explain 40 kg/second coming off a nucleus estimated between 5 and 6 kilometers across. Unless something else is happening. Near-infrared observations from Gemini South and NASA's Infrared Telescope facility caught hints of the answer. Ice debris floating in the coma itself. Not just vapor. Actual chunks of ice suspended in the clouds surrounding the nucleus. Once exposed to sunlight, even weak sunlight, those fragments heat up faster than surface ice because they have higher surface area to volume ratios. Each one becomes a miniature steam vent, hundreds or thousands of them scattered through the coma, all contributing to the total water output. The result looks like the nucleus is far more active than it actually is. Zexi Xing, the lead author, put it simply. Every interstellar comet so far has been a surprise. Oumuamua was dry, Boris was rich in carbon monoxide. And now Atlas is giving up water at a distance where we did not expect it. Each one is rewriting what we thought we knew. But why are those ice chunks there in the first place? Did 3I Atlas experience a fragmentation event before detection? Is this debris from millions of years of micrometeorite impacts during its interstellar journey? Or is this how comets from the thick disk of the galaxy naturally behave, their structure fundamentally different because they formed under conditions our solar system never experienced? The timing adds another layer. 3 Atlas faded from Swift's view in August, too close to the Sun for safe observation. But by early October, ES's Mars orbiters caught it during the flyby at 30 million kilometers. The coma was clearly visible several thousand km across, proving the activity was sustained. The comet is still hemorrhaging water as it approaches perihelion, and that is the critical word, approaches, because right now, 3I Atlas is entering solar conjunction. Earth and the comet are on opposite sides of the Sun. No ground-based telescope can track it through the glare. It will reach perihelion on October 29th at 1.36 astronomical units just inside Mars' orbit, completely hidden from our view. The solar radiation there will be orders of magnitude stronger than what Swift detected. If 40 kilograms per S was the baseline at 3 AU, what happens at 1.4? The textbook answer is straightforward. The comet should brighten dramatically. The coma should expand. Super volatile ices, things like carbon dioxide and carbon monoxide that sublimate at lower temperatures than water, should explode into space. The tail should grow into a spectacular streamer millions of km long. We've seen this pattern hundreds of times with solar system comets. But 3/2 Atlas has already shown it does not follow textbook predictions. The The water activity at 2.9 AU was not supposed to happen. The 8% active surface coverage was not supposed to happen. The icy debris field in the coma was not something we anticipated. So what happens during the hidden perihelion passage is genuinely unknown. The ESA's JUICE spacecraft will have the best view between November 2nd and 25th. After 3I Atlas emerges from behind the Sun, JUICE will observe with cameras, spectrometers, and particle sensors. The vantage point is unique, far enough from the Sun that the comet will be visible, but close enough to capture post-Perihelion activity in detail. The problem: data transmission. JUICE is using its high-gain antenna as a heat shield right now, relying on a slower backup antenna to send data back to Earth. We will not see those November observations until February 2026. 3 months of waiting. 3 months of not knowing if the comet survived perihelion intact, if it fragmented like Shoemaker-Levy 9 under Jupiter's tidal forces, or if something entirely unexpected occurred during those hidden days behind the Sun. There is another consideration, one that Dennis Boditz mentioned in passing but did not emphasize. Water is the universal yardstick of comet science. It is the baseline for measuring activity and inferring composition. But 3 Atlas is not a solar system comet. It is a messenger from another star's planetary system, one that formed potentially 10 billion years ago in the thick disk of our galaxy. The protoplanetary disk that gave birth to this object had different temperatures, different compositions, different chemical gradients than the one that formed Earth and Jupiter. The water we are detecting might be chemically identical to our own hydrogen and oxygen in the same familiar configuration, but the context is alien. The ratios of isotopes, the trace elements mixed in, the structure of the ice crystals themselves, all of that carries information about a star system we will never visit. Swift detected hydroxyl, the broken remnant of water molecules, but hydroxyl can also come from other parent molecules, organic compounds, alcohols, complex chemistry happening in the coma as sunlight and cosmic rays break apart larger molecules into fragments. The 40 kg/second might be pure water, or it might be a mix of water and other volatiles that produce similar spectral signatures. We need higher resolution spectroscopy to know for certain. We need longer observation windows. We need the comet to survive perihelion and remain active as it heads back out toward interstellar space, because that is the other reality. 3 Atlas is not coming back. After it passes Jupiter in March 2026, it leaves forever. This is our only chance to study a comet from the galactic thick disk, a population of ancient star systems we've never sampled before. Every observation matters. Every data point is irreplaceable. The fire hose of water is just the opening act. It tells us 3I Atlas is volatile rich, that it is structurally unusual, that it is actively outgassing at distances where solar system comets remain dormant. But the main event happens in the next month behind the Sun, hidden from view, where the rules of cometary behavior will either be confirmed or shattered completely. And when JUICE finally gets its observations in November, when the comet emerges into view with whatever perihelion did to it on full display, we will know if this water loss was a preview or a warning. We will see if 3 Atlas is just an exceptionally active comet or something that requires us to rewrite the textbooks entirely. The answer is waiting, hidden, 50 days away from revelation. Chapter 2. Lowe's Mothership Hypothesis. The Loeb scale rating changed from 4 to 6 in the span of 2 weeks. That is not a small jump. On a system where 0 means definitively natural and 10 means definitively technological, moving from 4 to 6 represents a fundamental shift in probability assessment, and Lowe does not make those changes likely. Each point on his scale requires quantifiable anomalies. statistical outliers that resist conventional explanation. By mid-August, 3I Atlas had accumulated enough of them to push the needle into territory that makes most astronomers deeply uncomfortable. Let me start with the trajectory probability that keeps getting cited and keeps getting dismissed. 0.005%. Those are the odds that a randomly entering interstellar object would pass as close as 3I Atlas does to Venus, Mars, and Jupiter, 5 in 100,000. Low and his team calculated this using orbital mechanics and timing windows, accounting for the fact that planets move and approach windows are narrow. The math is straightforward. An object on a retrograde hyperbolic orbit entering from the direction of Sagittarius has a tiny probability cone for each planetary encounter. The combined probability of hitting all three cones is vanishingly small. Critics argue that we're cherry-picking after the fact that if you look at enough interstellar objects, eventually one will have an unlikely trajectory just by chance. That is true. But we've only detected 3 interstellar visitors ever, and one of them just happened to thread a needle that gives it access to the 3 most interesting rocky bodies in the inner solar system. The Bayesian prior for that, the probability we should assign before even considering other evidence, is uncomfortable. Now add the perihelion timing, October 29th, solar conjunction, Earth and 3I Atlas on opposite sides of the Sun. No ground-based observation possible during the most critical phase. If you wanted to perform a propulsive maneuver, a burn that changes velocity in orbit, perihelion is the optimal location. You're moving fastest relative to the Sun, so every kilogram of propellant yields maximum delta 5. It is called the Orth effect. Spacecraft use it constantly, and 3I Atlas reaches perihelion precisely when we cannot see it. Low calculated the delta phi required for mini probes released at perihelion to reach Earth orbit. The numbers work. A small probe, maybe 10 kilograms, using a chemical propulsion system with specific impulse around 300 seconds, could perform a reverse Orth maneuver and insert itself into a stable orbit around Earth. Arrival window late November to early December, right when 3I Atlas emerges from behind the Sun, and we start looking for post-perihelion changes. Is this the plan? Is there a plan, or are we seeing patterns in randomness because humans are pattern-seeking machines and Loeb has primed us to look for exactly these patterns? The size discrepancy remains unresolved. Early brightness measurements suggested a 20 kilometers nucleus if the albedo was typical for asteroids. That is absurdly large for an interstellar object. Oumuamua was a few hundred meters. Boris was under a kilometer. A 20-click comet showing up in our solar system would be a statistical nightmare. The kind of event that should not happen in a human lifetime. But then Hubble resolved the coma and the estimates dropped. 5 to 6 kilometers based on the actual nucleus brightness versus the total system brightness, including dust. That is still big. That is still unusual, but is within the realm of the possibility for a natural object. Except the early brightness was not wrong. It was real. 3 Atlas genuinely appeared brighter than it should have for a 5 kilometers comet at that distance. Low suggests reflectivity. If the surface has metallic components, if the shape focuses reflected light, if the material properties are fundamentally different from porous ice and dust, you get anomalous brightness. You get an object that looks bigger than it is. That could be natural. Metallic asteroids exist. But combined with everything else, it adds weight to the probability scale. Then there is the dust configuration. Hubble images show maximum dust density on the sunward side. The heavy grains, the ones too massive for radiation pressure to push, are concentrated ahead of the nucleus in the direction of travel. Standard cometary outgassing should produce jets perpendicular to the surface based on local heating patterns. Those jets can point in any direction depending on the rotation axis and the distribution of volatile ices. But sustained sunward dust ejection requires either a very specific rotation pole orientation or something else. Something that continuously expels material in the direction of motion regardless of which hemisphere faces the Sun. Low points out this matches debris ejection from high-speed transit through the interstellar medium. If 3I Atlas has been travelling at 60 to 70 km per s for millions of years, impacts with interstellar hydrogen atoms are not trivial. Each impact releases energy. Enough impacts and you start eroding the leading surface. The dust we see could be impact ejecta, material continuously stripped off by ram pressure as the object ploughs through space. That is a natural explanation, but it is also consistent with venting from internal systems with attitude control thrusters, maintaining orientation with any number of technological processes that would produce similar observables. The rotation period of 16.16 hours sits right in the middle of ambiguity. Too slow to be spinning up from outgassing, too fast to be tidally locked to anything. For a rubble pile comet held together by weak gravity, the rotation is stable and unremarkable. For a solid object, natural or manufactured, the rotation is equally stable and unremarkable. It tells us nothing definitive. But the approach angle is harder to dismiss. Coming from Sagittarius means coming from the direction of the galactic centre, the most crowded, brightest region of the sky. Detection against that background is extraordinarily difficult. We only spotted 3I Atlas because Atlas survey telescopes are specifically designed to catch fast-moving objects, and even then it was nearly missed. Pre-discovery images go back to mid-June, but the object was barely visible at magnitude 20 a few weeks earlier, and we would have had no observations at all. It would have passed through the inner solar system completely undetected. If you are planning a reconnaissance mission to an alien solar system, approaching from the galactic centre is tactically sound. You arrive masked by background light, giving the inhabitants minimal warning. By the time detection occurs, you're already deep in the system, too late for any meaningful response. Is that what happened, or is this another case of retrofitting intent onto coincidence? The early spectroscopic confusion adds another data point. Multiple teams reported no carbon-based molecules in the first weeks. No clear water signature, just reddish dust and ambiguous absorption features. It looked active but not cometary. Lowe argued this was the smoking gun, the proof that 3 Atlas was not behaving like a natural comet. Then more observations came in. Water was detected. Carbon dioxide dominated the coma. The spectral signatures started matching cometary expectations. Lowe revised his position but noted the initial ambiguity remains unexplained. Why did it take so long for the comet to show standard volatile signatures? Why the early confusion? One possibility is observational bias. Early spectra were low-resolution short exposure taken when the comet was still faint. As it brightened and better instruments locked on, the data improved. What looked like an absence of volatiles was just an absence of sufficient signal-to-noise ratio. That is the boring answer. That is probably the correct answer, but probably is doing a lot of work in that sentence. Lowe is not claiming certainty. He's claiming we should look that the probability is non-zero, that the consequences of being wrong, of dismissing a technological artifact as a comet, because comets are common and artifacts are not, would be catastrophic for our understanding of intelligence in the universe. He wants the Galileo Project observatories monitoring for secondary evidence during November and December. If 3I Atlas releases probes, if those probes enter Earth's atmosphere to study our planet up close, there might be an uptick in unidentified aerial phenomena. Objects moving in ways that defy conventional aerodynamics, radar returns that do not match natural objects or human technology. Is this likely? No. Lowe admits the odds favour a natural comet, but the odds are not 100%. And in that gap between highly probable and absolutely certain lives, the entire field of technosignature research, we have spent 60 years listening for radio signals from alien civilizations, We have built massive telescopes to catch laser flashes from distant stars. We have analysed millions of stellar spectra looking for atmospheric biosignatures on exoplanets, but we've never seriously considered that artifacts might come to us, that interstellar objects, the very things we've started detecting in the last 8 years, might include probes alongside rocks. 3 Atlas is the test case, the object that forces us to develop methods for distinguishing natural from artificial at interstellar distances. And those methods do not exist yet. We have brightness curves and spectra and trajectory analysis. But we do not have a robust framework for saying this is definitely natural or this requires further investigation. LOWE is trying to build that framework in real time using 3i Atlas as the calibration target. The mothership hypothesis itself is elegant in a terrifying way. You do not send one probe to one star. That is inefficient. You send motherships on long, slow trajectories between interesting star systems. Each mothership carries dozens or hundreds of smaller probes. As it passes through a system, it releases probes tailored to study specific planets. The probes are expendable, small, cheap to manufacture. The mothership continues on to the next star and the next, mapping the galaxy over millions of years. From the perspective of the civilization that launched it, the return on investment is enormous. One mothership can survey thousands of systems, and we would never see it coming. The mothership itself would be dark, cold, indistinguishable from a comet or asteroid until it started releasing probes. By then, it is too late. The probes are already in flight, already approaching their targets, and even if we detected them, we could not intercept, not with current technology, not unless we had decades of warning. LOWE proposed a timeline. If probes were released on October 29th during the hidden perihelion passage, using reverse Orth maneuvers to slow down and capture into Earth orbit, they would arrive between November 21st and December 5th. We are talking about objects potentially the size of a shoebox, maybe smaller. With Earth's space surveillance network, we track objects down to about 10 centimeters in low Earth orbit. But that is for objects we expect to be there. Objects that follow predictable orbits, something entering from interstellar space. Something with active propulsion and maneuvering capability could easily evade detection. Would they make contact? Would they remain hidden? Would they study us from orbit or land on the surface or simply observe and report back? Those are the questions that keep LOWE awake at night because the answer determines everything. If they are peaceful explorers, the xenoarchaeologists of some ancient galactic civilization, then first contact could be the most important moment in human history. If they are something else, if the dark forest hypothesis is correct and revealing your location to the galaxy is a death sentence, then we might already be too late. The Galileo Project observatories will be watching. 3 sites, continuous monitoring, full sky coverage. Any anomalies during the November-December window will be documented, analysed, and published. If nothing happens, if 3 Atlas behaves like a comet and no probes arrive, then the hypothesis loses credibility. The Loeb scale rating drops back down. We file 3i Atlas under interesting but natural and move on. But if something does happen, if we detect objects that should not be there, moving in ways that should not be possible, appearing exactly when LOWE predicted they would appear, then we have a problem or an opportunity, depending on what comes next. Chapter the 3rd of October 29, Behind the Sun. Solar conjunction is not supposed to be this dramatic. Most comets pass behind the Sun, disappear from view for a few days or weeks, then emerge on the other side looking predictably different, brighter if they survived, fragmented if they did not. Astronomers have watched this pattern for centuries. We know what to expect, but 3 Atlas is reaching perihelion at 1.36 astronomical units on October the 29th, completely hidden behind the solar glare. And the uncertainty about what happens next is driving the community into uncharted territory. The geometry is cruel. Earth and the comet are on opposite sides of the Sun, with an angular separation that makes ground-based observation impossible. You cannot point a telescope at an object 12 degrees from the Sun without destroying the instrument or blinding the detectors. The solar glare overwhelms everything. Even space-based telescopes like Hubble have strict solar exclusion zones. SOHO and other coronagraphs might catch a glimpse, but 3E Atlas is expected to be too faint, too far from the solar limb to register against the scattered light. For approximately 6 weeks, from early October to mid-November, we are blind. But perihelion is not just about visibility, it is about physics. At 1.36 AU, the solar flux is intense enough to vaporize every volatile compound on the comet's surface. Water ice sublimates aggressively, carbon dioxide, which has been the dominant gas in the coma based on JWST observations, transitions from solid to vapor almost instantaneously. Carbon monoxide, ammonia, methane, any supervolatiles trapped in the ice matrix, all of them released simultaneously. The nucleus should become a pressure cooker. Gas escaping through cracks and vents, dust lifted by the expanding vapor, the coma swelling to millions a kilometre, the tail stretching behind like a banner. That is the model. That is what every textbook predicts. But the model assumes we understand the composition and structure of 3 Atlas. And we do not. Not really. The JWST data from August 6 revealed something unexpected. An 8:1 ratio of carbon dioxide to water. That is among the highest ever recorded for a comet. Most solar system comets show ratios closer to 1:1 or even water-dominated chemistry. Carbon dioxide is common but rarely the primary volatile. 3I Atlas flips that relationship. It is a dry ice comet with water as the secondary component. That changes everything about how perihelion should behave. Carbon dioxide ice sublimes at much lower temperatures than water ice. At 1.36 AU, the surface temperature on the sunward side could reach 200 Kelvin or higher. That is well above the sublimation point for CO2, which kicks in around 150 Kelvin. But water ice needs closer to 270 Kelvin to sublimate efficiently, so we get a decoupling. The carbon dioxide explodes off the surface immediately. The water buried underneath or mixed into the ice matrix sublimates more slowly. The result is a 2-stage outgassing event. First a massive burst of CO2 creating a bright, rapidly expanding coma, then a slower, sustained release of water vapor as the surface layers erode and expose deeper ice. But here is the complication. If the carbon dioxide dominates and erupts violently, it could blow away the surface dust layers that insulate the underlying water ice. Once that insulation is gone, solar radiation penetrates deeper, the water sublimation accelerates. The comet could transition from a CO2-dominated system to a water-dominated system in a matter of hours or days, and we will not see it happen. We will only see the aftermath when JUICE gets its observations in November. There is another scenario, one that nobody wants to discuss in formal papers but gets whispered about in conference calls. What if the comet fragment's perihelion stress is real? The combination of thermal shock, internal pressure from outgassing, and tidal forces from the sun's gravity can tear weakly bound objects apart. We've seen it happen. Shoemaker-Levy 9 shattered into more than 20 pieces before impacting Jupiter. Comet Bella split in the 1800s and never reformed. More recently, Comet Atlas, C2019. Y4 disintegrated in 2020 as it approached the Sun. Just fell apart into a cloud of debris. 3I Atlas has a rotation period of 16.16 hours. That is slow enough that centrifugal forces are negligible. Gravity should hold it together easily. But the object has been travelling through interstellar space for billions of years. Cosmic ray bombardment. Temperature cycling between near absolute zero and whatever warmth it absorbed, passing near other stars. Micrometeorite impacts. Internal voids from volatile loss over geological timescales. The structural integrity could be compromised in ways we cannot detect from spectroscopy or photometry. If it fragments, the light curve will tell us. A sudden brightening as more surface area gets exposed. Then a rapid fade as the fragments disperse and the total cross-section decreases. By the time JUICE observes in November, we would see multiple condensations separate nuclei, each with their own coma strung out along the orbital path. That would be spectacular from a scientific perspective. Multiple samples from the interior of an interstellar comet, different layers exposed, compositional gradients laid bare. But it would also mean we missed the fragmentation event itself, the moment of breakup, the forces involved, the way the material separated. All of that happened behind the sun where we could not document it. Then there is Lowe's scenario, the one that treats perihelion as an opportunity rather than a hazard. If 3 Atlas is technological, if it has any capability for propulsion or active maneuvering, perihelion is when you use it. The oath effect amplifies every kg of thrust. A small burn at perihelion produces velocity changes that would require orders of magnitude more fuel at a felon. If the goal is to release probes that capture interplanetary orbits, you release them here. The math is unambiguous. October 29th is the optimal window. Lowe calculated the exact parameters. A 10 kilograms probe with a chemical rocket providing 500 m/s delta-5 could insert into a highly elliptical Earth orbit with periapsis around 400 kilometers and apoapsis beyond the Moon. From that orbit, the probe could study Earth's atmosphere, oceans, electromagnetic emissions, anything visible from space. It could transmit data back to 3 Atlas before the mothership exits the solar system, or it could remain dormant, waiting, observing, recording for later retrieval. The arrival window is late November between the 21st and December 5th, depending on the exact release point and trajectory. That assumes the probes use minimal correction burns during transit. If they have more fuel, more sophisticated guidance systems, the arrival window expands. We could see them earlier or later. We could miss them entirely if they maneuver to avoid detection. And here is the uncomfortable question. Would we even recognize them? Our space surveillance network tracks catalogued objects, satellites, debris, spent rocket stages. We know where they are and where they should be based on orbital mechanics. Something new appearing in an unexpected orbit would trigger alerts. But the response time is not instantaneous. By the time we identified an anomaly, investigated its origin, ruled out natural explanations, the probe could have completed its primary mission and changed orbits again. Lowe has tasked the Galileo Project observatories to monitor for exactly this. 3 sites running continuous all-sky surveys in optical, infrared, and radio wavelengths. Any transient event, any object moving in ways that defy standard ballistic trajectories gets flagged for analysis. During the November-December window, the detection threshold will be lowered. False positives will increase, but so will sensitivity. If something arrives, they will see it. NASA and ESA have not officially commented on this aspect. Their focus remains on the natural comet hypothesis. But behind closed doors, people are paying attention. The space agencies have protocols for unidentified objects. Not UFO protocols, not alien contact scenarios, but engineering protocols for unexpected debris, untracked satellites, potential collisions. Those protocols can be adapted. If an object appears in Earth orbit with no launch history, no catalogue entry, no plausible natural origin, the protocols activate, tracking intensifies, military assets get involved. The international community starts asking questions. October 29th is 6 days away as this recording goes live. 3 Atlas is already invisible, swallowed by the solar glare. The last ground-based observations were in late September. Mars orbiters caught it during the October 3rd flyby. But those images showed a comet behaving normally, a visible coma, dust production consistent with solar heating. Nothing anomalous. Nothing that screamed technology or fragmentation or crisis. But perihelion is different. Perihelion is where the thermal stress peaks, where internal pressures exceed structural limits, where decisions get made, if decisions are possible, in 6 days. 3I Atlas will be closer to the Sun than it has been in its entire multi-billion existence. The surface temperature will spike, the outgassing rate will explode, and we will not see any of it. The only real-time data will come from heliospheric observatories. Parker's solar probe is nowhere near the right position, but Stereo and SOHO might catch something. Scattered light observations, brightness fluctuations. If 3 Atlas produces a major outburst, if the coma expands rapidly enough, the solar monitoring satellites could detect the change in scattered solar radiation. It would be indirect. It would be low resolution, but it would be something, a data point during the blind period. Then we wait for JUICE. The spacecraft is positioned perfectly for post-perihelion observations. Between November 2nd and 25th, it will observe with multiple instruments. Janus cameras for imaging, major spectrometer for compositional analysis, PEP particle detector for coma environment, UVS ultraviolet spectrograph for volatile identification. All of it pointed at 3 Atlas as it emerges from behind the Sun, still bright from perihelion heating, potentially fragmented, potentially trailing a spectacular tail, potentially doing something no one predicted. But the data will not arrive until February 2026. JUICE is using its high-gain antenna as a heat shield right now, relying on the medium-gain antenna for communication. The data rate is slow. Observations take priority over transmission, so the images and spectra get stored on board, queued for download when bandwidth allows. By the time we see what JUICE saw in November, 3I Atlas will be past Venus, heading back out toward the asteroid belt, already cooling and fading. 3 months of latency. 3 months of speculation and argument and competing interpretations. Did it survive? Did it fragment? Did anything unusual happen during the hidden perihelion passage? The answer exists right now in photons travelling from JUICE to Earth at light speed. But we cannot access it. We cannot know until the data arrives and gets processed and released to the community. That is the cost of observation at interstellar distances with solar system spacecraft. We get unprecedented views from unique vantage points, but we pay for it in time, in waiting, in uncertainty stretched across months instead of hours. October 29th is the inflection point. Before that date, 3 Atlas is a comet approaching the Sun, unusual but explicable, interesting, but not revolutionary. After that date, it becomes whatever perihelion made it, a fragmented debris field, a brightened comet with a massive tail, a dormant object that survived intact but inactive, or something else, something that requires new categories and new terminology and new frameworks for interpretation. The Sun hides the answer, not forever, just long enough to make the waiting unbearable. Chapter 4, The CO2 Anomaly. James Webb Space Telescope observed 3I Atlas on August 6th at 3.32 astronomical units from the Sun. The NISPEC instrument, designed to capture infrared signatures invisible to optical telescopes, recorded spectral images spanning 0.6 to 5.3 micrometers. What came back was not just unusual. It was a chemical profile that exists nowhere else in our observed comet catalogue. 7.661, that is the carbon dioxide to water mixing ratio. For context, the next highest recorded ratio, excluding the extreme outlier C2016, R2 sits below 3.1. 3I Atlas is not just rich in carbon dioxide. It is dominated by it to a degree that challenges our models of comet formation. Martin Cordner from NASA Goddard led the analysis team. The paper uploaded to a STIF in late August lays out the observations in detail. The coma shows enhanced outgassing on the sunward side exactly as expected from solar heating. Water is present. Carbon monoxide is present. Carbonyl sulfide shows up in tentative detections. Water ice appears in the spectral signatures. Dust scattering is visible in the near and 4-hour ED. All of it normal. All of it fitting comet behavior except for that ratio. 7.6161 is 4.5 sigma above the trend line for long period and Jupiter family comets at similar heliocentric distances. In statistical terms, sigma measures standard deviation. 1 sigma is normal variation. 2 sigmas notable. 3 sigmas rare. 4. 5 sigma something went very wrong or something is fundamentally different. When you get deviations that large, you start questioning whether your comparison sample is even relevant. Maybe 3i Atlas is not an outlier. Maybe it is a completely different population, and we are comparing apples to something that is not even fruit. The carbon isotope ratios offer another clue. Webb detected both carbon-12 and carbon-13 in the comet emissions. The ratio between them sits within the range found on Earth and in the solar system. That suggests the carbon formed in a similar stellar environment, not a population 3-star from the early universe where metallicity was near zero, not a carbon star enriched with unusual nuclear synthesis products, just normal carbon from a normal star. But the abundance of carbon dioxide relative to water tells a different story about where and how the ice formed. There are 2 primary explanations and both have problems. The first involves radiation processing. If 3e Atlas formed in a protoplanetary disk exposed to intense ultraviolet radiation from a hot young star, or if it spent billions of years in the interstellar medium being bombarded by cosmic rays, the water ice could have been preferentially destroyed. Water molecules are easier to break apart than carbon dioxide molecules. High-energy photons and particles hit the ice, cleave the hydrogen-oxygen bonds, and the freed hydrogen escapes into space because it is so light. The oxygen can recombine with carbon to form more carbon dioxide. Over geological timescales, an initially water-rich comet could become carbon dioxide-rich through sheer attrition. The problem with this explanation is quantitative. To shift a comet from roughly equal parts water and carbon dioxide to an 8:1 ratio, favouring CO2 requires extreme radiation exposure over extreme timescales. We are talking about billions of years in the interstellar medium with essentially no shielding. That is plausible for 3i Atlas given its potential age. But it also requires that the water ice remained exposed on the surface the entire time. If the comet has any protective dust layer, any internal structure that shields deeper ice from radiation, the processing efficiency drops dramatically. You get a gradient, surface ice heavily processed. Interior ice pristine. When the comet becomes active and starts shedding layers, the ratio should change as deeper material gets exposed. We have not seen that change yet. The ratio remained consistent between the August JWST observations and the earlier SphereX data. The second explanation involves formation location. Carbon dioxide has a lower condensation temperature than water. In a protoplanetary disk, there is a boundary called the CO2 ice line. Inside that line, carbon dioxide remains gaseous. Outside that line, it condenses into solid ice. The water ice line sits closer to the star. If 3i Atlas formed beyond the CO2 ice line in a disk where carbon was unusually abundant, it could naturally incorporate more carbon dioxide than water during accretion. The ratio gets frozen into the comet's composition from day one. This explanation requires specific conditions. A protoplanetary disk with a high carbon-to-oxygen ratio, or a disk where the temperature gradient placed the forming comet in a zone rich in CO2 ice, but depleted in water ice. Both scenarios are possible. Stellar metallicity varies, disk structure varies, but finding conditions that produce an 8:1 ratio is not trivial. You need fine-tuning. You need a star system that looks noticeably different from our own in ways that should be rare but not impossible. SphereX observations from mid-August provide supporting evidence. The Space Infrared Telescope detected a massive carbon dioxide cloud extending at least 348,000 km from the nucleus. No corresponding water cloud at similar scales. The CO2 is escaping faster, travelling farther, dominating the coma structure. Meanwhile, water production remained below detection limits for Sphere X with the upper bound around 4.5 kg/second. That is an order of magnitude below the swift detection of 40 kg/second, which itself was questionable given the distance and methodology. The discrepancy tells us something important. Water detection is hard. It requires specific wavelengths and specific instruments. Swift detected hydroxyl, the breakdown product, not water itself. Sphere X looked for water emission lines in the infrared and came up empty. JWST found water, but at lower abundance than carbon dioxide. Each telescope sees a different piece of the puzzle. Reconciling them requires assumptions about chemistry, photodissociation rate, and spatial distribution. None of those assumptions are well constrained for an interstellar comet with unknown composition. One detail from the JWST data stands out. The water emission at 2.7 micrometers shows spatial structure. It is not uniformly distributed in the coma. There are bright regions and dim regions suggesting localized sources, jets perhaps, or pockets of water-rich ice mixed into a carbon dioxide-dominated matrix. When those pockets get exposed to sunlight, they release water in bursts rather than steady sublimation. The result looks patchy in the spectral maps, the carbon dioxide emission at 4. 3 micrometers is smoother, more evenly distributed, consistent with widespread sublimation across the entire sunward hemisphere. That spatial difference has implications for the comet structure. If 3E Atlas is compositionally homogeneous, just carbon dioxide ice throughout, the outgassing should be uniform. The fact that water shows localized emission suggests heterogeneity. Chunks or layers or pockets of different composition mixed together like a geological formation with distinct strata, each layer recording a different epoch of the comet's formation or evolution. As the surface erodes, different layers get exposed and the gas production changes accordingly. But there is a competing interpretation. The localized water emission could be coming from the icy debris field in the coma, the same chunks that Swift indirectly detected through hydroxyl. If those fragments have different compositions than the nucleus, if some are water-rich while others are carbon dioxide-rich, the spatial variations make sense. You're not seeing structure on the nucleus. You're seeing structure in the clouds surrounding it, hundreds or thousands of ice chunks, each one a miniature comet, each one contributing to the total emission in different proportions. Distinguishing between these interpretations requires higher resolution imaging. We need to resolve the nucleus itself. See if there are active regions or jets or specific vents releasing gas. Hubble cannot do it. The nucleus is too small and too far away. JWST cannot do it. The field of view is too narrow and the comet is moving too fast for detailed mapping. JUICE might do it in November if the comet is bright enough and close enough and their cameras can track properly. But that is still uncertain. The carbonyl sulfide detection, tentative as it is, adds another layer. OCS is not common in solar system comets. It appears occasionally, usually in small quantities, and its presence suggests sulfur chemistry in the protoplanetary disk. If 3 Atlas has measurable OCS, it tells us the parent star system had sulfur available during planet formation. Combined with the carbon dioxide dominance, we are building a picture of a star system with unusual volatile ratios. High carbon, high sulfur, low oxygen, or at least lower water, a system where the chemistry leaned toward reduced compounds rather than oxidized ones. Why does that matter? Because volatile chemistry drives habitability. A star system rich in carbon dioxide and sulfur, but poor in water, is not a great place for life as we understand it. Water is the universal solvent. It is the medium where biochemistry happens. Carbon dioxide is useful. Plants use it for photosynthesis, but it does not replace water. If 3I Atlas formed in a system where water was scarce, any planets in that system would face severe challenges for developing or sustaining biology. They would be dry worlds, carbon-rich but water-poor. The kind of planets we've started finding around M dwarfs, those small red stars that dominate the galaxy numerically. Is that where 3 Atlas came from, in a dwarf system where the habitable zone was close to the star, where tidal locking baked one hemisphere and froze the other, where water remained scarce and carbon dioxide dominated the atmospheric chemistry? The thick disk origin supports this. Older stars, lower metallicity on average, but with wide variations, M dwarfs that formed 10 billion years ago and are still burning today unchanged, while the planets around them evolved or failed to evolve under harsh conditions. That is speculative. That is filling in gaps with assumptions piled on assumptions. But the chemistry does not lie. 7.61 is not a random number. It is a constraint, a boundary condition that any formation model has to satisfy. And satisfying it requires either extreme processing over billions of years or formation in an environment fundamentally different from the one that gave us Earth. The Jastandius-T observations ended in August. The comet moved too close to the Sun for safe observation, and the telescope shifted to other targets. There are no plans for follow-up observations post-perihelion. JWST time is precious, allocated months in advance, and the window for observing 3I Atlas is closed. Whatever happens at perihelion, whatever changes the chemistry undergoes during maximum solar heating, we will not see it with Webb. We rely on JUICE and ground-based telescopes to catch the aftermath. And by then, the CO2 to water ratio might have shifted. The coma chemistry might have evolved. The clues Webb captured in August might be the only snapshot we ever get of 3I Atlas in its pre-Rahelian state. That makes the data irreplaceable. A chemical fingerprint from an object that formed in another star system billions of years ago. A record of volatile abundances that reflect conditions we cannot replicate or directly observe. And a mystery that grows deeper the more we analyze it. Because 8.1 is not just unusual, it is a signpost, a marker saying something happened here that does not happen in our corner of the galaxy. Whether that something is natural or artificial, random or designed, remains the question that won't let go. Chapter 5. Mars Witnesses the Visitor. October 3rd, 2025. 3I Atlas swept past Mars at a separation of 29 million kilometers. For context, that is roughly 77 times the distance between Earth and our Moon. In cosmic terms, it is close. Close enough that ESA's Mars orbiters, machines designed to photograph rust-cold rocks a few hundred km below, could pivot their instruments skyward and catch the interstellar visitor as it blazed through Martian space at 67 km/s. The ExoMars Trace Gas Orbiter got the best shots. Cassius, the colour and stereo surface imaging system, captured a series of exposures between October 1st and 7th. The images are not spectacular by Hubble standards. 3 Atlas appears as a fuzzy white dot, slightly elongated, moving against a background of stree. The stars streak because Casses track the comet, compensating for its motion relative to the spacecraft. Each exposure was 3 minutes long. Stack them together and you get a crude animation, the dot descending through the frame. The coma clearly visible as a diffuse halo several thousand km across. No tail, or at least no tail bright enough to register above the noise threshold. Nick Thomas, principal investigator for CAs, admitted the observation was challenging. The comet is around 10,000 to 100,000 times fainter than our usual target. That target being Mars, a planet reflecting sunlight at close range. Pointing the same camera at a dim comet 30 million kilometers away is like using a microscope to look at the horizon. The instrument was never designed for this. The exposure times are wrong. The sensitivity is marginal, but they got it. A handful of pixels, a blob of light, confirmation that 3 Atlas was exactly where orbital mechanics said it should be, doing exactly what a comet does when it approaches the Sun. Mars Express, the older of the 2 ESA orbiters, attempted observations, but the comet proved too faint. The high-resolution stereo camera came up empty. The Omega and SpyCam spectrometers searched for spectral signatures, but the signal-to-noise ratio was too low for definitive detection. They might have caught something, a faint emission line, a subtle absorption feature, but the data is ambiguous, preliminary at best. The real value from Mars Express will come from the contextual geometry. Knowing exactly where the spacecraft was, exactly when it looked, and exactly what field of view it covered gives us constraints. If 3 Atlas had released smaller objects during the flyby, if fragments had separated from the nucleus, Mars Express should have seen them. The fact that it saw nothing except the primary object tells us fragmentation had not occurred yet. The comet was still intact. NASA's Mars orbiters were also watching. Mars Reconnaissance Orbiter, with its high-rise camera, has the resolution to potentially image the nucleus directly if the geometry aligned. The closest approach distance of 29 million kilometers translates to a spatial resolution of roughly 30 kilometers per pixel for high-rise. Given a nucleus estimated at 5 to 6 kilometers, that is marginal subpixel. The nucleus would appear as a brightness spike, a single overexposed pixel surrounded by the dimmer coma. But it should be detectable if the exposure settings were correct and the pointing was accurate. As of this recording, no high-risk images have been publicly released. That is not unusual. Processing Mars orbiter data takes time. The images queue up, get downlinked when bandwidth allows, pass through calibration pipelines, and eventually end up in the public archives. Weeks or months of latency is normal, but the lack of immediate release has fed speculation. Some corners of the internet insist NASA is withholding data. That Hooray saw something unexpected, and the images are being analysed privately before any public statement. That is nonsense. NASA does not work that way. The Mars missions are public programs with data release policies. Everything goes public eventually. The delay is operational, not conspiratorial, but the speculation highlights something important. People are paying attention. 3 Atlas has captured public imagination in ways that 1 IUA and 2 I Borisov never did. Maybe it is the timing. Maybe it is Lowe's provocative theories creating a narrative framework that sci-fi fans can latch onto. Maybe it is just that social media is more mature now, better at amplifying niche topics into mainstream awareness. Whatever the reason, the October 3rd flyby was not just an astronomical event, it was a cultural moment. People who've never looked through a telescope suddenly care about orbital mechanics and spectral analysis and the difference between a comet and a technological artifact. Perseverance. The NASA rover sitting in Jezero crater also attempted observations. The Mascom Z cameras can image objects in the Martian sky, stars, Phobos, Deimos, the Sun during eclipses, in theory. They could catch 3I Atlas if the comet was bright enough and high enough above the horizon during the rover's operational window. On October 1st, several MCAM-C images captured a faint streak in the sky. Simeon Schmaus, an astrophotographer, stacked those images and enhanced the contrast. The result shows a smudge where orbital predictions placed 3I Atlas. It is not definitive. It could be a cosmic ray hit. It could be image compression artifacts. But the position matches, the timing matches, and if it is real, it is the only ground-level view of an interstellar object ever captured from another planet. Avi posted about it, used it as evidence that the comet is trackable, observable, within reach of existing instruments if we just point them in the right direction. Others pushed back. The streak is too faint, too ambiguous. Extraordinary claims require extraordinary evidence, and a smudge and a stacked image does not clear that bar. But the debate itself is valuable. It forces people to engage with the data, to think critically about what constitutes proof versus possibility, to grapple with the uncertainty that defines the edge of discovery. China's Tianwen. One orbiter and UAE's Hope spacecraft were also positioned near Mars during the flyby. Both carry cameras and spectrometers. Both could theoretically observe 3 Atlas. No data from either mission has been released yet. Tianwen 1 operates under different data sharing protocols than NASA or ESA. Images and results filter out through academic papers and press releases on timelines that do not match Western expectations. Hope is more transparent, but its primary mission is atmospheric science, not deep space observation. If either spacecraft captured useful data, we will find out eventually. But the silence is not evidence of absence. It is just the nature of international space exploration, where coordination is imperfect and priorities vary. The Mars flyby was always going to be a snapshot. A brief window where geometry aligned and cameras could pivot skyward before returning to their primary missions. But that snapshot confirms critical details. 3 Atlas was intact. The coma was active and visible. The orbit matched predictions to within measurement uncertainties. No fragments, no secondary objects, no evidence of anything beyond a single comet on a hyperbolic trajectory doing what comets do, except for one detail that nobody is talking about publicly, but everyone is thinking about privately. The coma was larger than expected. Based on the solar flux at that distance and the estimated nucleus size, the coma should have been around 2 to 3000 km in diameter. CASIS images suggest 4 to 5000 km. That is not a huge discrepancy. Coma size estimates are notoriously uncertain. They depend on exposure time, detector sensitivity, how you define the boundary between coma and background. But it is larger than the models predict. Larger than it should be if the outgassing rate scales linearly with solar heating. Why larger? One explanation is that the nucleus is more active than assumed. That 8% surface coverage might be conservative. Maybe 10 or 12% is releasing volatiles driving a bigger coma than predicted. Another explanation is that the icy debris field is contributing. Those chunks floating in the coma, each one sublimating independently, expand the effective size of the outgassing region beyond the nucleus itself. A third explanation, the one nobody wants to voice but keeps surfacing in private conversations, is that 3 Atlas did something at Mars. Release material, vented gas, performed a maneuver that increased coma production temporarily. There is no evidence for the third explanation. None. But absence of evidence is not evidence of absence, and the Mars flyby was the last clear observation before perihelion. If something was going to happen, if probes were going to deploy or fragments separate, or the comet transform from dormant to active, the flyby window was the logical moment, close enough to planets to be interesting, far enough from the Sun that maneuvers remain efficient, hidden from direct Earth observation, but observable by spacecraft positioned at Mars. The fact that the Mars orbiters saw a normal comet with a slightly oversized coma is simultaneously reassuring and frustrating. Reassuring because it matches expectations. Frustrating because a slightly oversized coma is ambiguous enough to support multiple interpretations without confirming any of them. There is one more data point from Mars that has not been fully analyzed yet. The Nomad spectrometer on Trace Gas Orbiter did not just image 3 Atlas. It took spectra, low resolution, heavily contaminated by scattered sunlight and instrument noise, but spectra nonetheless. Those observations are still being processed. The team is working through calibration issues, trying to extract a signal from data that was never supposed to capture a target this faint and this fast. If they succeed, if Nomad managed to catch spectral lines from the coma during the flyby, we get composition data from a completely different vantage point than JWST or Hubble or Sphere X. Different viewing geometry, different phase angle, different illumination conditions, Any molecules that show up in NOMAD data can be cross-referenced against the earlier observations. Any molecules that are missing that should be there but are not become interesting. The results will not come quickly. Spectral analysis is painstaking work. Months of effort to extract meaningful science from marginal data. But the team is motivated. This is the kind of observation that defines careers. A once-in-a-lifetime chance to study an interstellar comet from Mars' orbit during closest approach. If they pull useful science out of those noisy spectra, it will be worth the wait. Mars also provided something else, a test of the tracking and coordination protocols. 3 2-due Atlas moved fast, 67 km per s relative to the Sun, though slower relative to Mars due to orbital mechanics. Pointing a spacecraft instrument at a moving target requires precise ephemerides. Real-time updates and perfect timing. The Mars orbiters nailed it. Cassis captured the comet right in the center of the frame. That success validates the methods. It proves we can coordinate observations across multiple spacecraft, multiple agencies targeting an object that gives us no second chances. And that matters for November. When JUICE observes post-Pallon, the coordination will be even more critical. The comet will be brighter, but also more active, potentially fragmented, potentially variable. JUICE will need accurate ephemerides updated in real time based on ground observations and orbital calculations. The Mars flyby was the dress rehearsal. JUICE is the main event and everything learned from the October 3rd observations. Every pointing procedure and calibration method and data processing pipeline feeds forward into making the November observations as scientifically productive as possible. 3I Atlas is gone from Mars now. The geometry shifted. The comet moved deeper into the inner solar system, closer to the Sun, further from the red planet. The orbiters returned to their normal routines, mapping surface features, analysing atmospheric composition, searching for subsurface water. The brief distraction of an interstellar visitor passed, and Mars returned to being just Mars, alone in its orbit, waiting for the next close encounter with something from beyond. Chapter 6. Will it break apart? Comet fragmentation is not rare. It is not even particularly unusual. Dozens of comets have disintegrated during recorded history, some spectacularly, some quietly, but all following a pattern that astronomers understand reasonably well. Thermal stress cracks the nucleus. Outgassing creates internal pressure. Rotation and tidal forces pull weakly bound material apart. The comet that was becomes the comet cloud that was, and we document it, analyse it, add it to the catalogue of objects that could not survive perihelion. 3 Atlas has no obligation to survive. That needs to be stated clearly. This is an object held together by gravity so weak you could escape it at a brisk jog. An object that has been thermally cycled between near absolute zero and whatever warmth it encountered during billions of years wandering the galaxy. An object porous and fractured and riddled with voids where volatiles once lived before sublimating away during previous stellar encounters we know nothing about. Structural integrity is questionable. Cohesion is marginal. The binding force keeping nucleus intact is measured in newtons, not megatons. So the question is not whether 3I Atlas could break apart. The question is whether it will, and the answer hinges on factors we cannot measure from Earth. Start with historical precedents. Shoemaker-Levy 9 is the famous case discovered in 1993, already fragmented into more than 20 distinct pieces strung out along its orbit like pearls on a string. The breakup happened in 1992 during a close pass by Jupiter. Tidal forces exceeded the comet's tensile strength. The nucleus pulled apart. By the time we detected it, fragmentation was complete. 18 months later, the fragments impacted Jupiter in a series of collisions that left dark scars visible for months. The largest fragment released energy equivalent to 6 million megatons of TNT, not from chemical explosives, just kinetic energy. Mass * velocity squared, 2. Physics does not care about your comfort level, but Shoemaker-Levy 9 was a Jupiter family comet. Small, loosely bound, already weakened by previous orbital passes. 3 Atlas is larger, denser, and this is its first and only pass through the inner solar system. Different circumstances, different risk factors. Comet 73 Pavasman, Vachman. 3 fragmented during the 1995 apparition, then fragmented again in 2006. Each passage passed the sun-shed pieces. By 2011, observations counted more than 60 distinct fragments, most of them tiny, all of them following similar orbits offset slightly by the velocity imparted during separation. The parent nucleus still exists, still orbits, but diminished, eroded, losing mass with each perihelion until eventually nothing remains but a debris stream. A meteor shower waiting to happen when Earth crosses that orbit centuries from now. Comet C 2019. Y4 Atlas, confusingly sharing part of its name with 3I Atlas, but completely unrelated. Disintegrated in April 2020, it was approaching its first perihelion, brightening as expected, generating excitement among amateur astronomers who thought it might become visible to the naked eye. Then it started fading rapidly. Within days, it went from a compact nucleus to a cloud of fragments too small to resolve individually. Hubble imaged the breakup. The fragments spread out, dimmed, disappeared. The comet ceased to exist as a coherent object. Nobody knows why C 2019 Y4 fragmented. It was not particularly close to the Sun yet. Tidal forces were negligible. Rotation was not extreme. Best guess is thermal stress. Rapid heating on the sunward side while the night side remained frozen created differential expansion. The nucleus cracked. Once cracked, outgassing exploited the weakness. Gas pressure from sublimating ice forced the crack wider. The process accelerated. Within hours or days, structural failure became catastrophic. Could that happen to 3I Atlas? Absolutely. The thermal gradient at perihelion will be severe. One side baking in direct solar radiation, the other side in shadow. Cold, barely affected. The temperature difference could reach hundreds of degrees Kelvin across a nucleus only 5 to 6 kilometers wide. That is a recipe for mechanical stress. Add internal pressure from carbon dioxide sublimation, which happens exclusively at the temperatures 3I Atlas will experience, and you have all the ingredients for a breakup event. But there is a counter-argument. 3IE Atlas has been active for months since at least June when pre-discovery images show a faint coma. The comet has been outgassing, releasing pressure, eroding its surface gradually. That slow erosion might actually prevent catastrophic failure. Think of it like a pressure relief valve. As long as gas can escape steadily through surface vents and cracks, internal pressure never builds to dangerous levels. The comet sheds volatiles at a controlled rate, losing mass, but maintaining structural integrity. The rotation period supports this 16. 16 hours is stable, not speeding up, not slowing down. If outgassing was uneven, if jets were firing asymmetrically, we would see changes in rotation rate as those jets impart torque on the nucleus. The fact that rotation remains constant suggests balanced outgassing, symmetrical erosion. The nucleus is not being torn apart by its own activity. Then there is the size advantage. Larger comets are harder to fragment. Gravity scales with mass. Tensile strength scales with cross-sectional area. For a 5 kilometers object, even one made of loosely consolidated ice and dust, gravity wins. The escape velocity is only a few meters, but that is enough to hold rubble together against rotation and moderate outgassing. You need a significant impulse to overcome that binding energy. A major outburst, a collision, a tidal encounter closer than 3I Atlas will experience. Unless the nucleus is already fractured, already compromised, a rubble pile held together by friction rather than cohesion. In that case, Even minor stress could trigger separation. The fragments would not fly apart violently. They would drift, slowly, diverging as their slightly different orbits caused them to separate over days and weeks. From a distance, it would look like the comet was fuzzing out, the nucleus becoming less distinct, the coma growing asymmetric. Eventually multiple condensations would appear, separate peaks in the brightness distribution, each one a fragment following its own trajectory, close to, but not identical with the original orbit. Yes, ExoMar images from October 3rd show no evidence of fragmentation at that point. The nucleus appears as a single brightness concentration, but resolution was poor. If fragments had separated by only a few km, Cassis would not have resolved them. They would still appear as one fuzzy blob. The only way to confirm integrity is through higher resolution imaging post-perihelion, and that falls to JUICE. Now, consider Lowe's alternative interpretation. What if fragmentation is not random? What if it is deliberate? A mothership reaching perihelion and releasing many probes looks from a distance identical to a comet breaking apart under thermal stress. You see multiple objects where there was one. You see them following divergent trajectories. You see brightness variations as the fragments tumble and present different cross-sections to the sun. All of it explainable by natural processes. All of it also explainable by intentional deployment. The difference is in the details. Natural fragments follow ballistic trajectories. Their orbits are determined entirely by the velocity they had at separation and the gravitational field they are moving through. You can predict where each fragment will be based on Newtonian mechanics. No surprises. Deployed probes, on the other hand, can maneuver. They have propulsion, guidance systems, the ability to change their trajectory after separation. If fragments appear that do not follow predicted ballistic paths, if they accelerate or decelerate or change direction, that is a technosignature, unambiguous, definitive. Lowe has called this the dandelion hypothesis, a mothership that disperses seeds, each seed a probe carrying sensors and communication equipment. The biological analogy is deliberate. Dandelions do not place their seeds carefully. They scatter them on the wind, relying on quantity over precision. Most seeds land in poor soil and die. A few find favourable conditions and thrive. For a technological civilization exploring the galaxy, the strategy is similar. Release hundreds of probes. Most fail or find nothing interesting. A few succeed and return data. The cost per probe is low. The potential return is enormous. If 3i Atlas follows this model, perihelion is the dispersal moment. The probes deploy. They use the sun's gravity and their own propulsion to reach target planets. Earth, Mars, Venus, maybe Europa or Enceladus if the mission profile includes icy moon surveys. Each probe has a specific destination and enough fuel to reach it. Within weeks or months, they arrive. Begin observations. Transmit data back to the mothership before it exits the solar system beyond communication range. From our perspective on Earth, we see what looks like a comet fragmenting. We analyze the pieces, calculate their orbits, publish papers about thermal stress and structural failure. And we miss the actual story playing out in real time because we assumed natural processes when something else was happening. That is the nightmare scenario for Lowe. Not that 3 Atlas is technological, but that it is technological, and we misinterpret the evidence because we're not looking for the right signatures. We've spent centuries studying comets. We know what comet fragmentation looks like. The knowledge biases interpretation. When we see fragments, we assume natural causes. Overcoming that bias requires deliberate effort, active searching for anomalies, tracking fragments more carefully than we would for a typical comet breakup, looking for trajectory changes, propulsive events, anything that deviates from ballistic motion. JUICE will do some of that automatically. The spacecraft tracks moving targets. It calculates ephemerades. If a fragment moves differently than predicted, the tracking software flags it, but the software expects small deviations due to outgassing, not large course corrections from propulsion. The threshold for anomaly detection is set for natural objects. Whether that threshold is sensitive enough to catch probe deployment is unknown. Nobody has tested it. Nobody has needed to. There is one more consideration. If 3Xi Atlas breaks apart naturally or artificially, we lose the primary target. Fragments are dimmer, harder to track. Spectroscopy becomes more difficult because the signal spreads across multiple objects. The opportunity to study an intact interstellar nucleus disappears. From a purely scientific perspective, fragmentation is the worst outcome. It means we do not get clean data on composition, structure, density. We get a debris cloud, interesting in its own way, but not the pristine sample we hoped for. But if it stays intact, if 3E Atlas survives perihelion as a single coherent object, we get that sample. JUICE observes it in November. Ground telescopes pick it up in December. We track it past Venus, past Earth's orbit, out toward the asteroid belt and beyond. We watch it fade as distance and reduced solar heating shut down the outgassing. We document the tail's evolution, the coma's dissipation, the return to dormancy, and we learn everything we can before it crosses Jupiter's orbit in March and leaves forever. So, the question stands, will it break apart? The answer arrives in November when JUICE gets its first clear view post-perihelion, when we see whether 3I Atlas is still one object or has become many, whether the nucleus survived or shattered. Whether this story ends with a whimper of dispersed fragments or continues with an intact comet carrying its secrets back into the darkness beyond. Chapter 7. The 10 Billion-Year Journey. Xavier Perez-Couto and his team at the University of A Coruña traced the trajectory backward. 10 million years of orbital integration using Gaia data on stellar positions and velocities. They were hunting for close encounters, stars that might have perturbed 3I Atlas during its long drift through the galaxy. Stars that could point back to its origin system. What they found instead was something more unsettling. Nothing perturbed it. 93 potential stellar encounters identified, 62 classified as high confidence, and not one of them changed the comet's trajectory in any meaningful way. Think about what that means. 10 million years of travel through the galactic disk through regions crowded with stars, dust clouds, molecular complexes, through spiral arms where stellar density peaks and gravitational interactions become unavoidable. And 3D Atlas just ploughed through all of it, essentially unaffected like a bullet 60 km/s, relative to the local standard of rest. Too fast for gravity wells to capture it, too massive for radiation pressure to deflect it. Just momentum carrying it forward on a path that has remained essentially unchanged for timescales longer than human civilization has existed. The velocity is the key. 3I Atlas is moving at 58 km/s in the galactic frame. For comparison, the Sun orbits the galactic center at around 220 km/s. Most stars in the solar neighborhood move at similar speeds, give or take 20 or 30 km/s. 3I Atlas is not just moving. It is moving differently. Its velocity vector does not match the local flow. It is not participating in the orderly rotation of the galactic disk. It is cutting across that rotation at a steep angle, which tells us it originated somewhere else, somewhere with different kinematics, different orbital properties. The thick disk is the obvious candidate. That population of ancient stars sandwiched around the thin disk where the Sun resides. Thick disk stars formed early in the galaxy's history when the Milky Way was smaller, more chaotic, less organized into the neat spiral structure we see today. They orbit with higher velocities perpendicular to the galactic plane. They dive up and down through the disk rather than staying confined to it. Their metallicity is lower on average because they formed from gas that had not yet been enriched by multiple generations of supernova. Matthew Hopkins and the Ottawa High Oxford team ran simulations, population modelling based on galactic structure and dynamics. Their conclusion, published in preprint form shortly after the comet's discovery, gave a 2/3 probability that 3I Atlas originated from the thick disk. Not certainty, not proof, just a statistical likelihood based on trajectory analysis and velocity matching. But 2/3 is high confidence in astrophysics, high enough to build hypotheses around, high enough to start making predictions. If 3 Atlas is from the thick disk, it is old. The thick disk stopped forming stars around 10 billion years ago. Any comet ejected from a thick disk planetary system has been wandering for most of the universe's current age. Our solar system is 4.6 billion years old. 3I Atlas could be more than twice that. It could have formed when the universe was less than 4 billion years old. During an epoch when star formation rates were peaking across all galaxies, when the cosmic landscape looked fundamentally different than it does now, 10 billion years of exposure to the interstellar medium, 10 billion years of cosmic ray bombardment, galactic cosmic rays, energetic particles accelerated by supernova shocks and active galactic nuclei slamming into the comet's surface at relativistic speeds. Each impact deposits energy, breaks chemical bonds, sputters away atoms over geological timescales. The damage accumulates, surface layers erode, chemistry changes, crystalline structure becomes amorphous. What started as pristine ice from a protoplanetary disk becomes radiation-processed material that barely resembles its original composition. Except for what is buried deep inside, cosmic rays penetrate only so far. The stopping distance in ice for a typical galactic cosmic ray proton is measured in meters, maybe tens of meters for the highest energy particles. But a 5 kilometers nucleus has plenty of shielding depth. The interior, protected by overlying layers, remains pristine, unaltered, a time capsule preserving the chemistry of a star system that formed when the Milky Way was young. That is what makes 3 Atlas scientifically priceless. It is not just old, it is a direct sample from the early galaxy, a piece of a protoplanetary disk that condensed into a comet while the thick disk was still actively forming stars. Everything we know about that epoch comes from indirect observations. Light from distant galaxies showing us what the universe looked like billions of years ago. Stellar archaeology in the Milky Way, where we analyze the chemistry of old stars to infer what the interstellar medium was like when they formed. Computer simulations of galaxy evolution that reproduce observed properties but carry enormous uncertainties. 3 Atlas is a physical artifact, not a simulation, not a distant observation, an actual object we can point telescopes at, an object that carries chemical signatures imprinted during formation, isotope ratios, organic molecules, crystalline structures in the ice, all of it preserving information about conditions in that primordial protoplanetary disk. The CO2 to water ratio becomes more significant in this context. An 8:1 ratio is not just unusual, it is a constraint on the formation environment. It tells us the parent star system had specific properties, high carbon abundance relative to oxygen or a temperature gradient in the protoplanetary disk that placed the comet's formation zone beyond the carbon dioxide ice line, but within a region where carbon was unusually available. Those conditions might be common in thick disk systems, or they might be rare. We have no statistics. 3I Atlas is our first thick disk comet. The sample size is 1, but 1 is infinitely better than 0. Before 3I Atlas, everything we knew about thick disk planet decimal populations was theoretical. Models predicted that those ancient star systems ejected comets and asteroids just like modern systems do. Predicted that some fraction of those objects would wander the galaxy for billions of years. Predicted that occasionally, statistically, inevitably, one were to pass through our solar system. 3-2 Atlas confirms the predictions, validates the models, proves that the early galaxy was forming planets and comets, and engaging in the same messy dynamical processes that characterize star systems today. The trajectory analysis also revealed something subtle. 3I Atlas is moving almost perpendicular to the galactic plane, its velocity component in the z direction. The direction out of the plane is unusually high. That is characteristic of thick disk objects. But it also means the comet has been oscillating up and down through the galaxy for billions of years. Each oscillation takes tens of millions of years, up through the thin disk, out into the galactic halo, back down through the disk, up again, a sinusoidal path that carries 3I Atlas through vastly different environments over its lifetime. Sometimes it is in the dense regions of the disk where star formation is active and supernova rates are high. Radiation exposure peaks. Dust impacts increase. The comet erodes faster. Sometimes it is in the halo in the nearly empty space between galaxies where radiation levels drop and impacts become rare. The comet goes dormant. Erosion slows to almost nothing. That cycling between harsh and benign environments might explain why 3I Atlas survived for 10 billion years. The halo phases gave it time to rest, to stop losing mass, to preserve its interior against the relentless grinding of interstellar travel. Shakru, Kakarov, and Avi published a comparative analysis. One Umuam, 2I Borisov, and 3 Atlas, 3 interstellar objects, 3 completely different origins. Umuam from the thin disk, young maybe 1 billion years old, Borisov intermediate around 1.7 billion years, also from the thin disk 3I Atlas, ancient median age 4.6 billion years but potentially much older from the thick disk. The diversity is stunning. It tells us interstellar objects are not a uniform population. They come from everywhere, all ages, all regions of the galaxy, each one carrying its own history. And if that diversity exists for the 3 objects we've detected, imagine what the full population looks like. The Vera Rubin Observatory, when it becomes fully operational, is expected to detect dozens of interstellar objects per year, maybe more. Each one will have a story, an origin, a trajectory through the galaxy that can be traced backward through simulation. We will build a census, map the distribution of ejected planetesimals across the Milky Way, learn which types of star systems are most efficient at ejecting material into interstellar space, which regions of the galaxy contribute most to the wandering population. 3I Atlas is the pathfinder, the object that demonstrates we can do this kind of archaeology, that we can take a comet discovered in July and by October have the reasonable hypothesis about where it came from and how old it is. The uncertainty is large. The error bars span billions of years. But the methodology works. Orbital integration plus population modelling plus chemical analysis equals origin story. Imperfect but improvable. There's one more implication that Perescuto mentions but does not emphasize. If 3I has been travelling for 10 billion years, it has visited other star systems, many other star systems. The galaxy rotates, stars move. Over 10 billion years, the comet has passed within a few light years of thousands or millions of stars. Some of those stars had planets. Some of those planets might have had life, and 3I Atlas sailed through these systems undetected or ignored, carrying its cargo of ancient ice onward to the next encounter. Which raises a question nobody wants to ask directly. If 3I Atlas visited other civilizations, if it passed through their solar systems the way it is passing through ours, what happened? Did they notice it? Did they study it? Did they ignore it as just another comet? Or did they do something else? Leave a marker, attach a probe, use it as a relay station for communication across interstellar distances. We have no evidence for any of that. None. But the absence of evidence is not dispositive when you're talking about events that might have happened 1 billion years ago around stars we cannot even identify. 3I Atlas could be carrying messages, data, technology. things placed there by civilizations that rose and fell while Earth was still a molten ball of rock, and we would not know unless we look closely with intent, willing to consider possibilities that sound absurd until you map out the timescales and realize absurd is not the same as impossible. 10 billion years is a long time, long enough for empires to rise and collapse, long enough for species to evolve intelligence and then go extinct, long enough for entire stellar populations to be born and die. 3 Atlas has been travelling through all of that, a silent witness to galactic history. And now for a few brief months, it is here passing through our system, giving us one chance to read whatever story it carries in its chemistry and structure, and maybe in modifications we've not detected yet because we're not looking for them. The trajectory continues past Jupiter in March, then out beyond the asteroid belt, beyond the Kuiper belt, beyond the Helop where the solar wind gives way to the interstellar medium, back into the darkness, back into the endless drift between stars. 10 billion years already travelled. 10 billion more to go until the galaxy itself changes beyond recognition. And 3E Atlas will still be out there moving, carrying its secrets, waiting for the next civilization to notice. Chapter 8. Scientists pushed back hard. Tom Statler did not mince words. NASA's lead scientist for solar system small bodies was asked directly about the technological artifact hypothesis during a media briefing. His response was blunt. It looks like a comet. It does comet things. It very, very strongly resembles in just about every way the comets that we know. The emphasis on very, very was deliberate. This was not diplomatic hedging. This was a scientist drawing a line and saying enough. The frustration in the astronomy community is palpable. Not because Loeb is asking questions. Questions are fine. Questions are what science runs on. The frustration comes from how these questions get amplified. How a hypothesis with low probability gets treated by media and social platforms as if it has equal weight to the mountain of evidence pointing toward natural origin. How every new observation, every spectrum, every image has to be filtered through the alien probe narrative before the actual science can be discussed. Chris Lintott at Oxford was even less diplomatic. He called the technological hypothesis absolute nonsense on stilts, an insult to the exciting work going on to understand this object. Lint was part of the team that traced 3I Atlas back to the thick disk. He has spent months analysing trajectory data, running population simulations, publishing results that advance our understanding of galactic dynamics and interstellar object origins. And then he watches those results get buried under headlines about alien motherships and mini-probes. The scientific community's investment in rigorous analysis gets overshadowed by speculation that requires no evidence and makes no testable predictions. Jason Wright at Penn State took a different approach. He wrote a detailed blog post systematically addressing each of Lowe's claimed anomalies point by point, data set by data set. Wright is not hostile to technosignature research. He works on it himself. He is part of the community searching for evidence of extraterrestrial intelligence. But he's also a careful scientist who insists on standards. And by those standards, 3 Atlas fails every test. Start with the brightness issue. The claim that early photometry suggested a 20 kilometers objective natural, therefore, it must be something else. Wright points out this is cherry-picking. The early observations were low resolution, taken when the comet was faint and distant. As better instruments got longer exposures, the size estimates converged on 5 to 6 kilometers. That is normal observational refinement, not a mystery requiring exotic explanations. The claim about missing cometary signatures in early spectra. Wright dug into those papers. The observations were marginal. Signal to noise barely above detection threshold. The absence of clear molecular lines was not proof of unusual composition. It was proof that the comet was too faint for definitive spectroscopy at that distance. Once JWST and other major instruments locked on, The signatures appeared: water, carbon dioxide, carbon monoxide, carbonyl sulfide, all exactly what you expect from a comet. The initial ambiguity was observational limitation, not physical reality. The trajectory probability of 0.005%. Write round the numbers independently. The calculation depends heavily on how you define close approach. If you use realistic detection thresholds, accounting for the fact that we can only see objects above certain brightness limits, the probability increases substantially. You're not calculating the odds of any random object passing near 3 planets. You're calculating the odds that an object bright enough to detect passes near 3 planets. That is a much less restrictive condition. The probability is still low, but not absurdly low, not 5 sigma anomalous. Then there is the dust configuration issue. The claim that sunward dust emission requires active propulsion or venting. Wright points to decades of cometary science showing that dust distributions are complex. Jet activity is never uniform. Rotation axis orientation matters. Local variations in volatile content create asymmetric outgassing. The specific pattern seen in 3E Atlas might be unusual, but it is within the range of natural behavior. Dozens of solar system comets show similar features. Nobody invokes alien technology to explain them. The rotation period argument falls apart under scrutiny. 16.16 hours is unremarkable for a comet this size. It is stable against breakup. It is consistent with either a rubble pile or a solid object. It tells us nothing about artificial versus natural origin because both would have similar rotation dynamics. Using it as evidence for technology is like saying a rock is artificial because it is round. Roundness can be natural or shaped. Rotation period can be natural or designed. The measurement itself is agnostic. Wright reserves his sharpest criticism for the approach angle argument. The claim that coming from Sagittarius from the direction of the galactic center is tactically smart for avoiding early detection. This is retrofitting intent onto geometry. 3 Atlas approached from that direction because that is the direction it was travelling. If it had come from Ursa Major, we would hear arguments about how that region is strategically optimal for some other reason. The logic is unfalsifiable. Any approach direction can be spun as intentional. That is not science. That is storytelling. But the most damaging critique comes from the absence of what should be there if the hypothesis were true. If 3D Atlas is a technological artifact, it should emit waste heat. Any active system, any electronics, any propulsion generates heat. That heat has to radiate away. At the wavelengths corresponding to a few hundred Kelvin, infrared telescope should detect thermal emission that does not match solar heating alone. Multiple infrared observations have been done, Spitzer before it was retired. JWST Sphere are ground-based infrared telescopes. All of them show thermal emission consistent with a cold icy body warmed by the sun. No excess, no anomaly, just a comet doing what comets do. If there is propulsion, we should see it spectroscopically, chemically. Trajectory changes that exceed what outgassing can produce. 3I Atlas has been tracked continuously since discovery. The orbit is known to high precision. Any deviation from a purely gravitational trajectory would be obvious. There is none. The comet is following Newtonian mechanics perfectly. No burns, no course corrections, no evidence of active control. If there is communication, we should detect it. Radio emissions, laser pulses, modulated light. The SETI community has been listening. Multiple radio telescopes have pointed at 3I Atlas during its approach. The Greenbank Telescope, the Allen Telescope Array, Parkes in Australia, all of them searching across wide frequency bands for any hint of artificial signal. The result is silence. Complete, total, not even ambiguous noise that would be interpreted generously. Just the background hiss of the universe with no artificial component. every test that could distinguish technology from a natural origin has been performed. Every test came back negative. At some point, the burden of proof shifts. It is no longer enough to point at low probability coincidences and demand that natural explanations account for them. You need positive evidence, a detection, a measurement, something that cannot be explained by a comet and requires invoking technology. That evidence does not exist. Statler made this point explicitly. We have extraordinary instruments. We've been observing 3I Atlas intensely for months. If there were anything genuinely anomalous, anything that broke the comet model in a way that required new physics or nuclear classifications, we would have found it. The fact that we have not is itself evidence, not proof, but evidence weighted heavily toward natural origin. The scientific community's response has been measured, but firm. Papers get published, data get shared, observations continue, but there is an unspoken agreement that the technological hypothesis does not warrant serious engagement anymore. It has been tested. It failed. Continuing to debate it is a distraction from the actual scientific opportunities 322 Atlas presents. Because those opportunities are immense. This is the first thick disk comet ever studied, the first object with an 81CO-21 ratio, the first interstellar visitor observed by JWST and SphereX and Mars orbiters simultaneously. The compositional data alone could refine models of planet formation in ancient star systems. The trajectory data improves our understanding of galactic dynamics and ejection mechanisms. The outgassing behavior challenges assumptions about cometary activity and volatile distribution. But all of that gets buried when the conversation keeps circling back to alien probes. Scientists are tired of it. Tired of spending time debunking claims that should never have gained traction. Tired of watching their work get ignored because it is not sensational enough. Tired of the implication that they are closed-minded for insisting on evidence before accepting extraordinary claims. Lindot's comment about insult is telling. The teams working on 3 Atlas are some of the best observational astronomers in the world. They're using cutting-edge instruments, publishing in top journals, doing exactly what science is supposed to do. Observe, analyze, draw conclusions based on data, and then they get told they're missing the obvious, that they are so wedded to conventional thinking they cannot see what is right in front of them. It is infuriating. There is also a deeper concern. The public takeaway from this entire episode is that scientists dismissed the alien hypothesis without properly investigating. That is backwards. The investigation was exhaustive. Multiple teams, multiple instruments, months of effort. The hypothesis was taken seriously, tested rigorously, and found wanting. But because the tests were technical, because the null results did not generate headlines, the public perception is that scientists are being dismissive rather than thorough. That perception damages science. It reinforces the idea that mainstream astronomy is too conservative, too afraid of paradigm shifts, too invested in protecting existing theories. And that is not true. Astronomers would love to find evidence of extraterrestrial technology. It would be the discovery of the millennium. Nobel Prizes, textbooks rewritten, a complete transformation of how we understand our place in the universe. The motivation is there. The will is there. What is missing is evidence. Wright summed it up in his blog post. The burden of extraordinary proof lies with extraordinary claims, not the other way around. Science does not work by demanding natural explanations. Provide absolute certainty before considering alternatives. It works by accumulating evidence and following it wherever it leads. And right now all the evidence leads to a comet. An unusual comet, an interesting comet, a scientifically valuable comet, but a comet. 3 Atlas will be observed through November and December. Tuesday will arrive in February. If something genuinely anomalous shows up, If the post-perihelion observations reveal behaviors that cannot be explained naturally, the conversation will change. Scientists will adapt. New hypotheses will be proposed. Testable predictions will be made. That is how science progresses through evidence, not speculation. Until then, the technological hypothesis remains what it has always been, a possibility with vanishingly low probability, unsupported by data, sustained by motivated reasoning rather than empirical foundation. And the scientists studying 3 Atlas will continue their work documenting this remarkable visitor from the thick disk, extracting every bit of information they can before it disappears back into interstellar space with or without the alien narrative, with or without the headlines, because that is what scientists do. Chapter 9. Social media goes wild. The panic started on TikTok. A video posted September 29th showed dramatic music over stock footage of comets and spacecraft. Text overlay claiming 3 Atlas was on a collision course with Earth. NASA hiding the truth. Impact expected October 22nd. The video got 2 million views in 48 hours. Thousands of comments. People making contingency plans, asking if they should evacuate, checking distances to nuclear bunkers, all based on complete fabrication. The collision claim was easy to debunk. 3 Atlas' closest approach to Earth is 1.8 astronomical units. That is 270 million kilometers, more than 1/2 times the Earth's sun distance. It never comes anywhere near us. The orbital mechanics are public. NASA publishes FMIDs. Anyone with basic software can verify the trajectory, but facts do not spread as fast as fear. The debunking videos got a few 100,000 views. The panic video kept circulating. Still does. Still generating comments from people who think October 22nd is doomsday. Then came the remote viewing claims. An account called NY Crypto King posted on X that they had remote viewed 3 Atlas, claimed to see structures inside, microbial life being carried in ice pockets, a signal broadcasting at frequencies we've not detected yet. The post included a detailed description of the interior composition, the arrangement of technological components disguised as natural materials, and a warning that probes would deploy on October the 29th, dropping microbes into Earth's atmosphere as part of a terraforming operation. Remote viewing is pseudoscience. Controlled experiments have repeatedly shown it does not work. Nobody can see distant objects through psychic means, but the post got traction anyway. 30,000 likes, 15,000 retweets. People treating it as credible intelligence, building theories around it, cross-referencing it with other conspiracy frameworks. The signal claim was particularly viral. Multiple amateur radio enthusiasts started monitoring frequencies they thought might carry the broadcast. They found nothing but convinced themselves the signal was encrypted or using modulation schemes beyond human technology. 4chan entered the conversation with a post claiming insider knowledge. An anonymous user identifying as a European astronomer said 3I is not a comet or a spaceship. It is a bubble of dark matter or dark energy left over from the Big Bang. The object does not reflect sunlight. It absorbs energy from the quantum vacuum. It is heading toward Earth to merge with the planet's core and trigger a dimensional shift. The post was obviously fiction. The physics made no sense. Dark matter does not form bubbles. It does not absorb vacuum energy. But the post got screenshotted and shared across platforms as if it were leaked classified information. The Jeffrey Epstein connection appeared in early October. Someone on Reddit noticed that Lowe's first major paper on 3 Atlas was published 72 years after Epstein's birth. They calculated that the comet's discovery date, July 1st, was significant in numerology, added some cherry-pick correlations between orbital parameters and dates relevant to Epstein's life, concluded that the entire 3I Atlas event was manufactured to distract from renewed interest in Epstein files, The conspiracy theory made no sense. Comets do not get discovered on predetermined dates to serve political agendas, but it spread anyway, blended into QAnon frameworks, got cited as evidence of deep state manipulation. Other variants targeted Loeb directly, post-claiming his analysis of 3 Atlas was discredited because of his Jewish heritage, because of Israeli connections, because Harvard receives funding from sources tied to whatever geopolitical enemy the poster wanted to invoke. These were not good faith criticisms. They were anti-Semitic attacks dressed up as skepticism. Lowe addressed them in a blog post, pointed out that 3 Atlas exists independent of his identity, that the object can be observed by anyone with a telescope, that his ethnicity and nationality have zero bearing on the physics, but engaging with bigotry is exhausting. The posts kept coming. The NASA shutdown angle became a major talking point. In early October, the US government shutdown began. NASA's Public Affairs Office stopped updating websites and social media. Press releases slowed. The temporary communication blackout coincided with 3I Atlas approaching Mars and slipping behind the Sun. Conspiracy theorists saw causation. The shutdown was deliberate. Time to prevent NASA from having to answer questions about what the Mars orbiters saw during the flyby. The agency was suppressing data, hiding images that showed fragmentation or probe deployment or something else they did not want public. In reality, government shutdowns are political failures, not calculated cover-ups. They happen when budget negotiations collapse. The timing was coincidental. NASA was not hiding anything. The Mars orbiter data takes weeks to process under normal circumstances. The shutdown delayed things further, but not because of censorship, because staff were furloughed and the pipeline stopped moving. When the government reopened, the images were released. They showed a comet exactly as expected. But by then, the narrative was set. The delay was proof of conspiracy regardless of what the data eventually showed. Alice's Sanad fact-checking unit investigated claims circulating in Arabic language social media, posts saying 3I Atlas would impact Earth on October 22nd, that its tail would poison the atmosphere, that electromagnetic pulses from the comet would disable all electronics globally. That religious prophecy predicted this event, and the signs were aligning. Sanad traced the claims back to mistranslations and deliberate fabrications, published detailed debunking with source citations and expert quotes. The fact-check reached maybe 10% of the audience the original false claims reached. A viral post on Facebook claimed 3 Atlas triggered a military emergency meeting. World leaders convened in secret. Defense systems were being activated. Quotes attributed to unnamed Pentagon officials suggesting the comet posed a national security threat. The post linked to a YouTube video. 3 million views, 40-minute run time. A narrator explaining how 3 Atlas was detected by classified military satellites before civilian astronomers saw it, how the trajectory was initially suppressed, how insiders leaked information through back channels, none of it true, all of it presented with ominous music and authoritative tone that made it feel credible. The religious angle became prominent, Christian posts interpreting 3 Atlas as a sign of end times, Revelation references wormwood connections, the comet as harbinger of judgment, Islamic posts discussing similar themes through different scriptural lenses, Hindu interpretations involving cosmic cycles and avatars, people across belief systems projecting apocalyptic narratives onto an object that is just ice and rock. The need to find meaning in celestial events is ancient. Comets have always been omens. 3 Atlas is no different, except now the omens spread globally in hours instead of taking years to filter through societies. Meme culture contributed. Images of 3 Atlas, labelled as various things. The homework I forgot to turn in finally showing up. My problems arriving right on schedule. Alien tourists coming to check if Earth is worth visiting and deciding to leave. The memes were harmless, often funny, but they reinforced the idea that 3E Atlas was a character in a story rather than a scientific object. That it had agency, intent, personality. The anthropomorphization made it harder to engage with the actual data. People were relating to the comet emotionally rather than analytically. The polarization was stark. On one side, astronomers and science communicators trying to share accurate information, spectra, orbital calculations, composition analysis. On the other side, a tsunami of speculation, conspiracy, fear, and wishful thinking. The two groups barely overlapped. They occupied different information ecosystems, different platforms, different epistemic standards. A person could spend hours consuming content about 3I Atlas and never encounter a single accurate fact. Twitter community notes tried to keep up, adding context to viral posts, linking to NASA pages, providing orbital data to counter collision claims, but community notes only appears after a post has already gone viral. The correction reaches a fraction of the audience. And motivated reasoning is powerful. People who want to believe in the alien mothership hypothesis find ways to dismiss corrections. NASA is lying. Scientists are closed-minded. The official story does not add up. Anything that contradicts the preferred narrative gets filtered out. YouTube became a battleground. Science channels trying to explain what 3I Atlas actually is, what the observations show, what the chemistry means. Those videos struggle to break a 100,000 views. Meanwhile, conspiracy channels with dramatic thumbnails and sensational titles pulled millions. The algorithm favors engagement over accuracy. Fear drives engagement more effectively than education. So, the misinformation gets promoted, amplified, monetized. Reddit communities split along predictable lines. The astronomy and space subreddits maintain sanity. Moderators removing conspiracy posts. Users debunking claims with citations. Civil discussion about trajectory uncertainties and spectroscopic methods. But other subreddits, the ones focused on UFOs and conspiracy and fringe topics, became echo chambers. Any skepticism got downvoted. Any link to mainstream science got dismissed as propaganda. The communities self-radicalized, convinced each other that they understood the truth while everyone else was blind or complicit. Instagram influencers with no scientific background posted confident explanations of 3E Atlas. Many got basic facts wrong, confused astronomical units with light years, claimed the comet was visible to naked eye when it never was, mixed up 3 Atlas with other objects. But they had audiences, hundreds of thousands of followers who trusted them, who shared their posts, who treated influencer speculation as equivalent to peer-reviewed research. The misinformation had real consequences. Astronomy educators fielding panicked emails, teachers trying to calm students who thought the world was ending, mental health professionals dealing with anxiety triggered by apocalyptic narratives. The damage was not hypothetical. It was measurable, quantifiable in the time wasted correcting falsehoods and the psychological distress inflicted on vulnerable people. Some of the conspiracy thinking was performance trolling. People who knew better but enjoyed creating chaos. But some of it was genuine. True believers convinced that 3 Atlas represented first contact or existential threat or divine intervention. Those people doubled down when contradicted, sought out information that confirmed their views, built elaborate frameworks connecting 3I Atlas to other conspiracies. The object became a symbol, a blank screen onto which people projected whatever fears or hopes or fantasies they carried. By mid-October, 3I Atlas had transcended its identity as a comet. It was a cultural phenomenon, a mirror reflecting how society processes information in the age of social media. how truth and fiction blend, how expertise gets devalued, how fear spreads faster than understanding. The actual object, the 5 kilometers ball of ancient ice and rock currently hidden behind the sun, became almost irrelevant to the narrative swirling around it. And the scientists studying 3 Atlas could only watch. They could publish papers, give interviews, post corrections, but they could not control the story. The story had escaped, mutated, become something beyond their reach. All they could do was continue the work, document the observations, analyze the data, trust that eventually, long after the social media frenzy faded, the scientific record would remain accurate, preserved, a counterweight to the chaos. Chapter 10. November's Moment of Truth. JUICE is positioned 428,000 km from 3 Atlas on November 4th. That is closer than any spacecraft will get during the post-perihelion observation window. The Jupiter Icy Moons Explorer was not designed for comet observation. It is built to study Europa, Ganymede and Callisto, ice crusts over subsurface oceans, radiation environments around Jupiter, magnetic field interactions, but spacecraft are adaptable. Mission planners can pivot. And between November 2nd and 25th, JUICE will dedicate observation time to the interstellar visitor, capturing data at a moment when ground-based telescopes still struggle with solar proximity. The instrument suite is formidable. Janus, the optical camera system, will image the nucleus and coma at resolutions no other spacecraft can match during this period. MAGIS, the imaging spectrometer, will map composition across infrared wavelengths, tracking how different volatiles distribute in the coma. UVS, the ultraviolet spectrograph, will detect emissions from excited atoms and molecules, building on the swift observations from August, but with higher spectral resolution. PEP, the particle environment package, will measure the plasma and neutral gas surrounding 3 Atlas, documenting how solar wind interacts with the comet's outgassing. This is the critical window. 3 Atlas emerged from perihelion on October the 29th. Whatever happened during that closest approach to the Sun, the maximum heating, the peak outgassing, the potential fragmentation or probe deployment, the evidence will be visible in November. The comet should be bright, active, possibly changed. JUICE will document that change from a vantage point Earth-based instruments cannot replicate. But there is a constraint: communication bandwidth. JUICE is using its medium-gain antenna because the high-gain antenna is currently serving as a heat shield. Data transmission rates are reduced. Images and spectra get stored on board, downloaded when time allows. The November observations will not reach Earth until February 2026. 3 months of latency. 3 months where we will not know what JUICE saw, whether the comet survived intact, whether it fragmented, whether anything unexpected appeared in the data. Ground-based observatories will pick up 3I Atlas in late November, when the solar elongation increases enough that twilight observations become possible, when the comet clears the worst of the glare and becomes accessible to large aperture telescopes. The predictions vary. Some models suggest magnitude 10 or 11 bright enough for 8 in amateur telescopes under dark skies. Other models are more conservative, predicting magnitude 12 to 13 requiring professional instruments or dedicated amateur setups. The brightness will tell us immediately if something major happened. If 3E Atlas brightened dramatically, if the perihelion passage triggered a massive outburst or exposed fresh volatiles, the magnitude will be higher than predicted. If it fragmented, the total brightness might increase initially as more surface area gets exposed, then drop as the fragments disperse. If it went dormant, if the volatiles exhausted or the activity shut down unexpectedly, it will be dimmer than expected. All of that becomes apparent in the first few nights of ground observations. The Galileo Project observatories are operational. 3 sites monitoring the sky continuously. Massachusetts, Pennsylvania, Nevada during November and December. Detection thresholds are lowered. Any transient object, any unidentified moving target gets flagged. Lobers made no secret of his expectations. If probes was deployed at perihelion, if they used reverse Orth maneuvers to insert into Earth orbit, they arrived between November 21st and December 5th. The observatories are watching for exactly that. Small objects in unusual orbits, trajectories that do not match catalogued satellites or debris, anything that suggests artificial origin. The probability is low. Everyone acknowledges that. But the cost of watching is minimal compared to the potential payoff. If something appears, if an object shows up that cannot be explained naturally, the game changes immediately, dramatically. Every telescope in the world would pivot to study it. Space agencies would scramble to plan intercepts or close observations. The scientific community would mobilize in ways we have not seen since the first gravitational wave detection or the first exoplanet confirmation. And if nothing appears, if November and December pass and no probes materialize, then the technological hypothesis loses its last remaining support. The Loeb scale rating drops. 3 Atlas gets classified definitively as natural comet, unusually large and chemically anomalous. But natural nonetheless. The speculation ends, the science continues. The story becomes one of discovery and characterization rather than alien contact. Europa Clipper is also positioned for potential observations. NASA's mission to Jupiter launched recently. The spacecraft is en route but not yet at Jupiter. Coordination between Clipper and JUICE is being discussed. Both have ultraviolet spectrographs observing 3I Atlas from 2 different locations, simultaneously provides parallax stereo observation 3-dimensional information about coma structure that single spacecraft cannot obtain. The geometry is not ideal. Clipper is not optimally positioned, but if the opportunity exists, mission planners will take it. The real science comes from comparing pre- and post-perihelion states. We have August data from JWST, September data from Mars orbiters. Those observations captured 3I Atlas approaching perihelion, still relatively cold, outgassing at moderate rates. The November data from JUICE and ground telescopes will show the aftermath. The comet heated, stressed, potentially transformed by the closest solar encounter of its 10 billion year existence. Comparing those data sets reveals how interstellar comets respond to perihelion, how their chemistry evolves, how their structure holds up or fails under thermal shock. The CO2 to water ratio becomes particularly interesting. In August it was 8:1. Will it still be 8:1 in November, or will perihelion heating have preferentially driven off the carbon dioxide, leaving water ice exposed and shifting the ratio towards something more typical? If the ratio changes, it tells us the comet has a layered structure. Carbon dioxide-rich outer layers, water-rich interior. If the ratio stays constant, it suggests homogeneous composition throughout. Both outcomes are scientifically valuable, but they tell very different stories about how this object formed and evolved. The tail development is another diagnostic. Preparian images showed a faint tail or no tail depending on exposure time and instrument sensitivity. Post-perihelion, the tail should be prominent millions of km long, curved by solar radiation pressure, and the orbital velocity spectroscopy of the tail reveals what dust grains are being ejected Silicate Organics ices. The grain size distribution tells us about the erosion processes. Small grains mean vigorous sublimation. Large grains mean mechanical disruption or explosive events. If 3E Atlas fragmented, the tail will show complexity, multiple streams, overlapping structures, each fragment contributing its own tail, all of them blending together in ground-based images, but potentially resolvable with careful photometry and positional measurements. Hubble could theoretically image the tail structure if telescope time becomes available, resolve individual fragment contributions, map the debris distribution, but Hubble time is precious. Oversubscribed by factors of 5 or 10, getting directors discretionary time for a follow-up observation is not guaranteed. The Vera Rubin Observatory is not operational yet. Its first light is still months away, but when it comes online, it will revolutionize interstellar object detection and characterization. The Large Synoptic Survey Telescope, as it was originally named, will scan the entire visible sky every few nights. Deep exposures, automatic detection of moving objects. Rubin will catch interstellar visitors earlier when they are still far from the sun and faint, and it will track them through perihelion and beyond, build light curves with thousands of data points. Spectroscopic follow-up with other instruments will be informed by detailed photometry from Rubin's continuous monitoring. 3 Atlas is the prototype, the object that teaches us what to expect from future interstellar comets, what their brightening curves look like, how their activity evolves, what spectral features appear and when. Every observation of 3I Atlas informs survey design for Rubin, refines his detection algorithms, calibrates models. The next 3 Atlas, the 4th interstellar object, will be detected faster and characterized better because of lessons learned from this one. The November observations also matter for trajectory refinement. Every position measurement improves the orbital solution, reduces uncertainties, allows better predictions of where 3 Atlas will be in December, January and beyond, as the comet moves past Venus, past Earth's orbit, heading back toward the asteroid belt. Tracking becomes harder. It dims, moves against increasingly crowded starfields. Having precise ephemerides ensures we do not lose it. That ground telescopes can point accurately. That observing time does not get wasted searching for an object that should be in the field of view but is not because the coordinates are slightly off. The plasma environment measurements from JUICE are unique. No other spacecraft will be close enough to sample the interaction region where solar wind meets cometary outgassing. That boundary, the comet pores, is dynamic, constantly shifting as outging rates change and solar wind pressure varies. PEP will measure ion densities, electron temperatures, magnetic field perturbations, all of it feeding into models of how cometary magnetospheres work, how charged particles accelerate, how energy gets deposited into the coma. For 3I Atlas specifically, the plasma data might reveal something subtle about composition. Different volatiles ionize at different rates, produce different ion species. The mass spectrometer component of PEP can distinguish between water group ions, carbon dioxide group ions, and others. If unexpected species appear, if the plasma composition shows molecules that were not detected spectroscopically, that is new information. Additional constraints on what is actually present versus what we inferred from remote observations. February 2026 feels distant. 3 months is a long time to wait for JUICE data, but it is also necessary. The spacecraft has limited bandwidth. Science takes priority over public relations. The data will be worth the wait, processed, calibrated, analyzed by experts who understand the instruments and know how to extract signal from noise. When the results are published, they will be definitive. The best post-Perryian characterization of 3I Atlas we can possibly obtain given current technology and mission constraints. Until then, we rely on ground observations, amateur astronomers with backyard telescopes, professional observatories squeezing 3I Atlas into crowded schedules, spectroscopic campaigns organized through international collaboration. Every clear night matters. Every observation adds to the data set, and slowly, image by image, spectrum by spectrum, the story of what happened at perihelion comes into focus. The comet does not care about our curiosity. It does not know we are watching. It simply continues its trajectory, outgassing or dormant, intact or fragmented, Natural or against all probability? Something else. 3 Atlas moves through November, oblivious to the telescopes tracking it, the instruments dissecting its light, the debates raging about its nature. It just is. And we, from our tiny vantage point 93 million miles from the Sun, try desperately to understand what that means before the comet disappears into the dark and takes its answers with it.